So, hi guys, I'm Gautaman. I'm a AI researcher in CellSat, and the topic that we are going to be seeing today is MLOps model monitoring. So, MLOps has different stages. One of the key aspects in MLOps is model monitoring. We will be seeing what are the different options in model monitoring, what are the features that we can be seeing. We will take a particular example, which is weights and biases tool, and see how the model can be monitored. And also after the presentation, we can also I will share the code. We can run it and see how the model is being logged for two particular examples. So the first thing that we'll be seeing is how the MLOps flow is being done, and the second is how the model monitoring happens, and the tool that we will be using is weights and biases. And in weights and biases, two particular tools we'll be using, which is sweeps and artifacts. So these are two of the important features. And sweeps allows us for hyperparameter tuning, and artifacts. This is being used both for the model and data versioning. So how this is being accomplished, we'll be seeing in the upcoming slides. So MLOps, MLOps gives us the practices which makes the data and model management easier. So here, if you see, this is a key structuring of how the ML ops model is being planned. First thing that we do is we monitor the model. So how the model behaves, what are the different parameters in it, and how that affects our metrics, and what are the changes that we could be doing to get the optimal model. So that is where the model monitoring happens. And then is the configuration management and the data version control. So these things happen so that we can configure what are the different parameters that we have in the pipeline, and what are the versions that we need to be controlling, uh, so that this is in a more organized manner, and we can be more effectively maintaining our pipeline. The next thing is the model packaging. So model packaging is also important because we could be building in a different framework, and that could be deployed in a different framework, and it could also be the case where it could be trained in a uh, GPU laptop, and it could be deployed in a mobile software. So these kinds of edge devices are a different framework. We need to be taking it into account, and for that we need to be knowing about model packaging. The next thing is the continuous integration and continuous deployment. So our code, we always try to improve it, and that we need to be continuously integrating our improved code in our repository, and we need to also be deploying it. So that we need to be knowing. And the next thing is the container registry and the serverless deployment. So the container registry is more to do with the Dockers, and the serverless deployment to do with Lambda. These become a crucial future when we need to deploy the model that we have built. And the last is the prediction monitoring. So how our model behaves, how the data changes. For example, a data model drift happens. So how do we integrate changes into our pipeline so that the flow is smooth. So these are the different things that we need to be taking into account when we build the model. So today we'll be seeing about the first thing, which is the model monitoring. So why model monitoring? So we will be building a model, and there are different challenges while building a model. First thing is we need to be understanding which is the most optimal parameters that gives us the best metrics, and also we need to be trying different model configurations. And we also need to be seeing different model and input data versions, and which particular data version and which model gives us the best possible outcomes. So these things, if if we do a series of experiments and if we collaborate with the team, it, we need to be making it as a log data so that it will be easier for us to backtrack and see which of our configurations gave us the best metrics. So that's why logging the whole pipeline becomes a very essential part, and and that gives us the better and faster insights. So, why the model monitoring? First thing is the understand the accuracy of the predictions. So, how our accuracy of the predictions matters, and what are the different things that we can change that in turn affects our accuracy. The second thing is prevent the prediction errors, so that we will be knowing which versioning and which versioning of the data and the model gives us the best predictions, and also tweaking the model. So which parts of the parameters we can be changing so that we can have a good boost in the metrics. So these things, if we need to be knowing, we need to be logging the whole pipeline, and that's where the model monitoring comes into picture. So model monitoring, there is a lot of libraries and tools that offer us this particular setup, model monitoring. One of the most common things is TensorBoard. So people have used TensorFlow. So this is one of the things, like TensorBoard gives us the logging the model parameters. So we'll be knowing in that particular run how the model has behaved. There are several other tools that helps us in model monitoring. One is Comet, the second is MLFlow, the third is Neptune, TensorBoard, and weights and biases. So these are the different common tools that people have been using for the model monitoring. And today we'll be seeing about one particular tool, which is the weights and biases. So, to give a little bit of a background on weights and biases, so this is essentially a model monitoring tool. So what are the things that it will do? It will track our experiments. So, what are the experiments that we are doing? It will have a log of all those experiments. It will have a data set and model versioning. So, what are the different data set and model that we have? It will create an artifact. So, the term that is being used is artifact. So, it will create an artifact for that, so that we can easily be knowing which data set and model that we have been using. So, the first thing is the experiment tracking. So, if we need to do different experiments, for example, image classification, so that is an experiment. So that could have some hundreds of runs. So each run, what is the different parameters that we use and what is the metric that is being achieved, we can be going to those particular individual runs and understand those. So that experiment tracking is a feature that is there. The second thing is the reports. It also gives reports of experiments. So if there is a case where, let's take for example, data science team is there, the different members of the data science team needs to understand how they are going about their approach, and they need to make the collaborative discussions so that they can move forward their process. So here the reports comes into picture because it helps us to visually understand how different approaches have been and which would be the optimized approach going forward. The next thing is the dataset and model versioning. So this becomes a very important because we need to be having artifacts. So these are the dataset and model is being considered as an artifact, a material that is being saved in the repository. So this should have different versions because only then we will be knowing what is the different uh, for example, a futurization, normalization, standardization. So we do these for the data sets. So when these are being made, what is that impact on the model? We need to be understanding. So each thing what we try, we version it so that we'll be able to know which version gives us the optimized results. So that is where the artifacts comes into the picture. And there is also a data visualization component. So each of these things, for example, the loss or accuracy or different epochs or different steps, how it has behaved. So that kind of interactive data visualization is also available in weights and biases. And the last thing is the hyperparameter optimization. So in our models, we could have tens of hundreds of hyperparameters, and we need to be coming up with the best configuration that gives us the results. So there we will be using this hyperparameter optimization. In this particular lecture, we will be seeing about these two things, which is the artifacts and sweeps, and how that could be accomplished. So Bayesian biases is being used by a lot of ML practitioners like NVIDIA, OpenAI, Lyft, Fujifilm, Toyota, Samsung. So a lot of people use this because it gives a structured way of going about our approach, and it's easy to track our experiments. So the two things that we'll be seeing today is sweeps and artifacts. The sweeps is the tool in weights and biases that helps us in hyperparameter tuning. So to make automated hyperparameter optimization, we use the sweeps. So what is the use of sweeps? The first thing is it's a quick setup. We don't need tens of hundreds of lines of code. We just need to specify the sweep that we going to be launching, and this sweep will be act as a master node, and it will have a lot of worker nodes where the splitting will happen. I'll explain that more on the upcoming slide. So you can easily launch the sweep across dozens of machines. So this quick setup is one of the uses. The second thing is it's open source. The backend code that they are using is open source, so it's more of a transparent thing. And the third thing is it's very customizable and configurable. So whatever the changes that we want in our model to be logged, and what are the different approach of the hyperparameter tuning that we want, everything could be set in a config file, which in turn will be taken by the model. So it's very customizable and configurable. So that's why sweeps is easier to use. So what are these some of these use cases of sweeps? The first is the parameter importance. So we use sweeps to know which parameter is of utmost importance. So when we build a neural network, there are different parameters that could affect our neural network. One is learning rate, dropout, batch size, channels, epochs. So each of these things, how it affects, we'll be knowing. So here in the backend, they are using a random forest split to know which parameters of utmost importance. So and a correlation matrix by which they are knowing for a particular metric how the correlation with each of these parameters is. So we could be easily knowing with this tables how our different parameters are affecting our metrics and accuracy. So parameter importance to be easily known with sweeps. The second thing is exploring the different hyperparameter combinations. So we in sweeps will be using different combinations of parameters. For example, the learning rate decay. So the learning rate decay could have a bunch of values, the category, the learning rate. So each thing in our neural network could have a bunch of values. So that in turn, how it affects our accuracy. So that we should be knowing with sweeps. So here, if we see, if let's take for example here, it has a learning rate decay of 0.04, and here it takes a value of 4, and this again goes and takes a value of 0.3, and that in turn takes a value of 0.9. So if we take a bunch of values, how it would result in, we could be easily knowing with this exploration charts. So this is another use case of sweeps. The next thing is the early stopping. So the sweep gives us the early stopping mechanism. So we will be able to specify when to stop for our model. And for example, let's take for example, let us stop it if it has achieved some 0.95 accuracy. So what it will do is it will always try to make the most promising and best performing runs. So an experiment will have a bunch of runs. In the hyperparameter tuning, each run will have different parameters, and these parameters will be worked out for the model to train. So the early stopping condition, how we give based on that, if it is not performing, for example, if there are some five runs and there are two runs that is not performing well, it will do a early stopping and it will prevent the model from training further. In this way, we could be saving the computational cost for our resources, and we could be what are the good and better performing parameters that will be wholly trained, and that parameters will get logged. So that in that way, the early stopping helps us a lot. The next thing is the massive scale. So again, this is a very distributed way of computing. So because it's a distributed way of computing, so each run uh, we could be having it in a massive scale. So sweeps, it can handle massive scale because it's doing a parallel computing. So in the parallel computing, it will assign each run its own resources, so that we could be scaling up very easily. So here, if we see, there are a bunch of runs that is happening, and each has its own runtime, epochs, accuracy. So we could be easily knowing which run has which type of parameters, and these runs will be happening parallelly, because here the parallel compute is happening in sweeps. So how do we use sweeps? I will also tell in the code how we use the sweep. So basically, what we do is, first thing is we add the weights and biases. So that is van B. So we add the weights and biases. The next thing is we need to write the configuration. So what is the configuration in which we need to be searching for the hyperparameters? There are different strategies. Uh, some of them is grid, random, and Bayesian search. So I'll explain how these things are done, and what are the different parameters that we need to be taking, and values. So every thing in that would be specified in the configuration file. The next thing is we need to be
So,
initialized. Yeah.
yeah, Gautaman, in TensorBoard also we were adding serialization code, right, within the Python code, right?
Yeah.
So that will create some kind of serial files
Uh,
which are analyzed by TensorBoard.
uh,
So it looks like a similar scheme here, right?
yeah. So as I was
Okay,
said before, TensorBoard is also one of the model monitoring tools.
right. So weights and biases is kind of far more comprehensive
Yeah,
than
it will be
so.
yeah, a lot more
Okay.
user friendly.
So it does need code changes where we have to write instrumentation code which will produce some
Yes.
introspection files,
Yeah.
right? Okay, okay,
Not a lot of codes, but yeah, we need to be adding
okay.
code for this. So initializing the sweep. So we initialize the sweeps server. So this will be a central controller that will be coordinating with all the other agents to execute the sweep. So we initialize the sweep. The next thing is we launch the agents. So once we launch the agents, every individual agent will have its own run, and that will again send the data back to the central controller. And with that, we will be able to know how the hyperparameters have behaved. And once we do it, the weights and biases will be giving us the link, and we could be seeing in those links how our model has performed. So visualizing those results is also one of the key components in sweeps. So I'll also tell how this adding the weights and biases, doing the configuration for file, initializing, launching, and visualization in the code. So this is how the distributed computing happens in sweeps. So what it does is, it will have a central sweep server, and it is split into different agents, and each agent will be assigned its own task, and asynchronously they will be doing their task, and getting back their hyperparameters. For example, we say learning rate and the dropout as two hyperparameters. So it will take two values from a configure file, how high we have assigned. It will take two random values and give to the first agent. Again, two values of this to the second, and here. And each agent will have its own run and will observe how these parameters are affecting the accuracy. That will get logged in the weights and biases, and again that will be sent. The data will be sent back to the central sweep server. So in this way, the distributed computing helps us in using the resources judiciously and scaling up very efficiently. So what are the different search methods that we can be using for our hyperparameter tuning? So the first thing is the grid search. So grid search, it is very effective, but also very computationally costly. Why it is that is like, let's take for example, there are three parameters that we need to be taking, and we give for each parameter some two values. It will be 2 power 3. So, and if there are 10 parameters, it will become 2 power, n parameters, it will become 2 power n. And if there is like each parameter has some 10 values, so it will become exponentially increasing. And what the grid search does is it iterates over every combination of the hyperparameter. So even though it checks for all the runs, it is checking that by going through all the values that we have assigned. So when this happens, it becomes very computationally costly, and it is not one of the very preferred methods while we do our hyperparameter tuning. The next thing is the random search. Random search, what it does is it takes random values for each of these parameters, and for those distributions, check for the metrics. So even though it makes a random check of the values, and with that assigns the values, it is surprisingly effective, and it is one of the most common methods by which we do the hyperparameter tuning. The third thing is the Bayesian search. Bayesian search, what it does is it does a probabilistic model for the metric score as a function of hyperparameters. So what it does is it chooses hyperparameters that give that will give a high probability of a good metric. So in this way, for example, if there are 10 different values, if it finds two values that gives a better metric, it will have a higher probability of choosing those values. And though it's very effective for models that are very small, when it becomes bigger and bigger, it doesn't scale, and it only scales very poorly. So these are the different searches by which we can be doing the hyperparameter tuning. In our case, we will be doing a random search. This is about the sweeps. So sweeps is for the hyperparameter tuning, but also show in the code how that is being done. The another key component that is being used in weights and biases is artifacts. So artifacts is essentially for the versioning, to version all our data sets and models. So whether we want to store the files with the weights and biases, or if we have some buckets where we save it, we can easily track them with the artifacts tool. So the artifacts, how it is being saved in weights and biases, I will show during the code. So what it does is it does a directed graph. Essentially, it's a bipartite directed acyclic graph. So graph, it has nodes as the artifacts and runs, and the arrows connecting the runs to the artifacts. So essentially, what it does is it tells us how to version different models and data in our own way. So we could be able to make a custom modifications for our models and data and version them. And once we version them, what it does is it creates a graph for those artifacts and tells this artifact whether it's input of any run or output of the different run, and it will give you a process flow of that in the weights and biases tool. So we can easily track which is the model and which is the data that we are using. So that's where the artifact is being used. So here, this is the workflow for the artifact. So here, what we are doing is, this is the image classification example. So here, the image data set, that is an artifact. So this image that, so this is artifact of type data set. What we do is we do a run, which is the training the model to classify the images. So that we do with van init and use artifact and log the artifact. So once we specify these commands, we will be getting the model, which will be the trained model. This trained model is again an artifact of type model. So in this way, the data sets and models we could be saving with our own specification and versioning, that will be able to use it easily in further and future experiments. So what are the use cases of artifacts? The first thing is it's effective observability. Trace the flow of the data through a pipeline. So here, as I told, it makes a graph for those artifacts that we create. So we'll be able to easily know how our versioning model is there, and in which way that has been connected to other runs. So it gives us the option of effective observability. And the second thing is incremental tracking. So while we do the experiment, we will have hundreds of runs, and each thing will create, for example, so each thing will create its own artifact. So those artifacts, for example, here they have three specified artifacts. So each artifact will be able to know in which pipeline it has been and how that has performed. For example, if this particular run has given the most effective metric, so in which way we have modified our artifacts to get to this point, we will be able to easily track those things. That's why artifacts are easier. So this is about the artifacts. So we have the sweeps and artifacts in the W weights and biases tool that we'll be seeing. I'll also show the code demo so that it will be even more clearer. Vic, could you share those files?
Yeah, I'll provide the Google Drive link
Yeah.
for the two notebooks, right? They're just two notebooks, right?
Yeah.
Okay, just a moment. Let me find those in my Google Drive.
Yeah. You guys can download it and run it parallelly so that we'll be able to know.
So hyperparameter tuning sweeps and data model versioning.
Yeah.
Here. Copy link. So folks, I'm sending the two notebooks here. You can download them. Share. Copy link. So there are two notebooks which have been shared in Google Chat now. So please download them, and you can run them in Colab, or you can run them in Self-Set Hub. We have not tested it in Self-Set Hub. We would like to. Didn't get a chance to do that yet. But meanwhile, it should run in Google Colab. So feel free to ask any questions if you are facing any challenge in downloading those notebooks. I have shared them. Very quiet audience today. Not many questions so far. Okay, so meanwhile, Gautaman, maybe you can just continue while
Yeah,
the
okay.
folks try to run them in Colab or Cellstrat Hub, as the case may be.
Yeah, okay, sure. So the first thing that we need to be doing, installing the weights and biases tool, and the code that I will show is, first I will show about sweeps. The second thing I will show about the artifacts.
There's a question by Bhavesh. Can it be used to monitor models that are deployed elsewhere?
Um, yes. So anywhere we
Yes.
can be using it. So we need to be adding the weights and biases code. So that in turn will get saved there.
No, deployed models. Can it monitor deployed models?
Deployed models. Uh,
In
yeah, I
Cellstrat Hub,
don't.
we are deploying APIs,
Uh,
but Bhavesh, the problem is this architecture needs code instrumentation. You have to change the model code, and it will produce serialized file. So weights and biases is not a real-time monitor, right? It's a offline monitor once the
yes, yes.
serialized files have been produced. Same as TensorBoard.
Yeah.
So does weights and biases have any aspect of real-time monitoring, even if I have added the code in the model before deployment?
Yeah, I don't think it's for the deployed models. Here,
Okay.
these two tools is for training the models.
Got it. So same as TensorBoard,
Uh,
purely during training, and you have to edit the code. Okay.
yeah.
Okay, fine.
So first thing is like installing the libraries. So weights and biases I will install. And this particular case, it's MS dataset. We need that dataset. We'll also be downloading that. Uh, yeah, I have just a couple of minutes. I'll rejoin now.
Let me send the two links again, which I sent on chat. Just a moment, please. I'm sending the shared Google Drive links again on chat. Okay, here you go. So you can download these, upload it into your Google Drive, and open it in Colab.
Hello. Yeah. Hi, guys.
Yeah, yeah, Gautaman, are you back? Please
Yeah, yeah,
increase your volume.
yeah. Can you hear me now?
Volume is a little low.
Uh, yeah. I'll just speak
No,
for
it's
two or
okay
three
now.
minutes.
Yeah, it's okay now.
Uh, so here, the first thing is we have installed this, and second thing is we need to be logging into the directory of weights and biases. So this will be done by this. So here, what it does is it's trying to uh, asking to authenticate this.
So it will do a real-time authentication with weights and biases.
Yeah, so we
Oh,
can directly link it. So whatever we do here, that will be logged in the weights and biases.
oh, it's a cloud-based tool, huh? It's not okay.
Yeah.
Interesting. In TensorBoard, it's all local,
Yes,
but
yes.
but
Yeah.
here it's a purely cloud-based tool. Okay.
Yeah. So now we have logged into the weights and biases. So the next thing that we'll be doing is we need to be specifying in which way our search needs to be there. As I told previously, there are three different ways: random, grid search, and Bayesian search. So we need to be telling in which type our search needs to be done. So here we will be telling it's a random search. And the next thing that we'll be telling is what are the different parameters that we need in your hyperparameter tuning. For example, the optimizer, it could be either Adam or SGE. The fully content layer size, it could be something like 128, 256, 512. And a dropout, how much the value could be. It could be a 0.3, 0.4, or 0.5. So this thing too we will be detailing, and we will be adding that into our sweep configuration. So sweep configuration, we have added the method, and now we are adding the parameter dictionary into the parameters. Again, parameters dictionary, we also update our epochs. So as this is just a test run, we are adding an epoch of value 1. The next thing is the learning rate and the batch size. So learning rate and the batch size, unlike other values like optimizer or FC layer size, we will be adding it as a distribution. So this will be a learning rate will be a flat uniform distribution between the values of 0 and 0.1. And for the batch size, we have this Q log uniform, which means that it will be in different orders. So the batch size will be of different orders. So it will be anything, the integers between 32 and 256 in 2 power order it will be. So that we are specifying. So we will be adding this into our parameters dictionary. We will check once our sweep configuration. So here we will be getting our sweep configuration, which has what is the method that we are using, what are the different parameters that we have been using. So we have specified how we need to be checking the method and each of our parameters in which values we need to be checking. So once we have done this, the next thing that we need to be doing is we need to be initializing the weight and bias sweep. So I will specify this as sweeps. Yeah, just the sweeps I will specify. W and B sweeps. So I'll specify the sweep as a Van B sweeps, and so this is the project name that I have given, and the configuration that I have that I will be initializing the sweep. So I have initialized. So this gives me a sweep URL. I'll be able to go there and see how my sweep is. So now we haven't done anything. So there is still nothing being done, but a sweep has been initialized for me as I have given that.
So there is a question on chat.
Yeah.
If you see the chat in Google Meet.
Just a minute.
By Gopinath.
Hello.
Yeah.
Yeah. So before doing the sweep for hyperparameters,
Hi.
do we have to do like manual seed and feed it to the model, or the want B will take care of it? Is it like even in
Yeah.
when I do model execution,
Yeah.
every time I'm getting the results different, even if I set the manual seed.
Okay. Speed should give you the same results, I think. You're telling about the hyperparameter tuning to have the same values.
Yes.
Uh,
So the hyperparameter sweep depends on the accuracy, right? Like you are trying to get the hyperparameters, set of hyperparameters for best accuracy, right?
yeah.
That best accuracy depends on the weights again for that set
Yeah.
of, yeah.
Uh,
So when the weights changes, I mean, no, it's random, right? When we initialize the weights, if it starts from the random different values, it may not optimize as we wanted, right?
Weight, I think the weight initialization, we could be giving a particular thing.
Mm.
Uh, so that won't change is what I think. Because this only deals with the hyperparameters. So whatever the weights is, this will get. So if it's a particular weight initialization method, the hyperparameters is going to give you the same results or close to the same results. Like it will give
Okay,
you idea of which range of values would be better.
okay. Thank you.
Right. So we have initialized the sweep. The next thing is we need to be training the model. So here, so we import what are the libraries, PyTorch libraries that we need. We check for a CPU or GPU, so that we do. The next thing is we train the model. So training the model, uh, what we do is we give the band B in it. So we give the configuration. So the configuration happens, and then we specify three functions: build dataset, build network, and build optimizer. These things just for better like structuring, they have made it as three functions. We could make it as a single function and specify this. So here they are doing a build data set. So build their data set, what it does is it does the data transform. So here it converts into tensor, does the normalization. The next thing is it downloads the data set, and it does a data loader and returns the data. So this is the build data set config battery. So once we have the data set, the next thing is the build network. So we'll be specifying the whole network that we need. So we are giving a simple neural network architecture. So here it's a sequential, flattened, fully controlled linear layer, a dropout, again a linear layer, and a softmax layer. So this is the build network. So once we have the loader that we'll be building the network with this and getting the network, and we'll also be building an optimizer. So again, build optimizer. So based on our what configuration we have, it will select the optimizer and return the optimizer. So we'll have the loader for the data, the network for the model, and what is the optimizer that is being used for the optimizer, and for how much epoch that we have specified, the train epoch, and we have this thing. So the train epoch function will be this thing. This is a normal PyTorch parse where it takes the data, it makes the optimizer to zero gradients, and it does the forward pass for the loss, and then it finds the loss, and with that it tries to update the weight and log that batch loss into our weights and biases tool and return our cumulative loss. So that is what the train epoch happens. So that is what happens here, and it will give us the average loss. And so for each epoch, we will be knowing what is the loss and in which epoch it happens. So that's what this code is about. So we have done that. The functions that is being used there, as I explained before, is what this cell is. So that too we have ran. The next thing is now we have the whole network. we will be telling it to use the sweep ID. So this will launch this sweep and count is 5. So there will be 5 different runs with the hyperparameters that we have specified and this training model. So each run will be logged into our weights and biases that we can be tracking. So what it has done is the first run it has completed. So from our config file, it has taken some random search values. So batch size, dropout, epoch, FC layer, learning rate, optimizer. So it has taken its own values for this particular run. And for that, how the metrics have been achieved, that it will get logged to our the bandwidth tool. So this is the first run. The second run has been completed. In the third run, each run, it also gives a link for each run. So we could be seeing how it is. So here it has given the sweep page. You can go to this sweep page. So there are 5 sweeps that has happened. So we have told it to try for 5 things. So it has tried for 5 things. So here it gives the basic information of sweep. This is the sweep ID and it has what is our config file values. So we have specified this random, batch size, how in which distribution we need, dropout, how we need, epochs, how we need, uh, fully connected layer, how we need, learning rate, how we need, optimizer, how we need. So that will be logged here. The next thing is the sweep in itself. So there are 5 sweeps. Each sweep we can go in turn into that particular run, and see how, for example, here it's just because it's only one epoch, it has one value for the epoch and loss. The batch loss, how it has happened, each step that we'll be able to know. So here if we see, so here in this sweep thing, we could be able to we need to be editing this panel. We can add our loss function. So we have this batch loss. We will add that batch loss. Okay. So I have added this batch loss. So now if we see, we'll be able to know with which different trajectories how our ultimate loss is there. So here there is a less of a loss happening at 0.6 here. So this trajectory, if we track back, we will be able to know which is the optimizer that is being used. So here it is Adam, and here it takes a learning rate between 0.025, and that has a C layer around some 260, and that again has a dropout of 0.3, and it has a very high batch size of 132. So we could be able to know here which trajectories gives us the optimized metrics. So here it is 5 runs, so it is having this. So if we make some yeah, huge model with a lot of hyperparameters, there will be hundreds of runs. So each so in that we could be easily detecting which pattern gives us the optimized metric. That is the one thing. Also, we could be
I think weights as biases has done a very neat thing in putting it on cloud. So if they give you that link, you go there, no need for any local install anything.
yeah. So here if you see, there is this add panel. So here we could be adding whatever charts that we need for exploration. For example, as I told, parameter importance are another interesting thing they have done. So here we will be able to know for our metric which is the most important parameters that is affecting our metric. In this particular case, if it's batch loss, so the most important parameter that is affecting that is batch size. Second is dropout. Third is FC layer size, and after that it's almost not much of a difference. So even the correlation, how it is doing, whether it's a negative correlation or it's positive correlation with our metric, you will be able to see that.
Mm.
So these are the things that you'll be able to see with our hyperparameter tuning.
Can you just explain that big chart again quickly?
This
What is
one.
this indicating? Yeah.
So we have in our config file a lot of different values for hyperparameters, right?
Mm.
So batch size, dropout, FC layer, learning rate. So we have specified the method as random search. So based on that, it has taken some values. So those values, we have specified some 5 runs. So in that 5 runs, how the so this is a particular trajectory that with a ticker line. So this is telling which values uses which metric. So if we need a particular loss to be small, then we could see here if we see. So we can select that trajectory and see which values it has taken for that. So in this way, we will be able to know which particular hyperparameter range with each parameter would give us a very good metric. So here, if you see, it tells the run name as floral sweep 2. So there is this floral sweep 2. So in that, which is the hyperparameters it has taken and which is the metric it has got. So that
So
is
how will we arrive at best models or artifacts? There is a question here.
yes. So this is sweeps. So hyperparameter tuning is essentially to know which hyperparameters will give us the best. So here, if we want the best batch loss, so here this particular trajectory gives us. So we'll be able to know this batch size. The values here would give us the optimized model. So this is just for 5 runs. So if we need to make an exhaustive thing, we can run it for some 500,000. So then there'll be a lot of trajectories, and which trajectories gives us the optimized metric. We can find the ranges in each of this, and from that we can be arriving at our optimized model.
So from looking at this, we arrive at what should is the ideal batch size, dropout, FC layer size, right?
Ah, yes.
We are arriving at those ideal figures.
Yeah,
So
yeah.
as per this chart you are seeing, what are the ideal figures you think?
Yeah, this thing, okay, this thing, losses, this thing gives the least loss. Actually, both the runs gives the least loss. I'll take one thing. So the run name is Royal Suite. The batch size they have taken is 177. The dropout is 0.5. FC layer size is 256. Learning rate is 0.08. And optimizer is HGD.
So this is the best combo as per this.
Yeah. So this is how we could be arriving at the optimized parameters with sweeps.
And this is pretty cool. See, we run a lot of academic classes and workshops, right?
Uh,
But we have toy data sets, toy programs, or academic learning only. So we don't care that much. But the
yeah,
moment we go to production grade application with huge data sets,
yeah,
parameter tuning will become paramount to get the right performance. So that's when I think this is very useful.
yeah. So this is about the sweeps. I will also tell about the artifacts. Artifacts, again, we need to be installing the libraries for that. we're importing the weights and biases. The next thing is here. So here in artifacts, they are using this random seeds and specifying those random seeds for the reproducibility. So the thing that here in artifacts, what we need to be doing is we need to be specifying this is the data set and saving that as an artifact. So each time we need to be at each step, for example, the raw data, after the data pre-processing, before the pre-trained model, the trained model. So each thing will be saved as a separate artifact. So that it will be easier for us to manage those resources. So here, if we see, we need to be importing the libraries and after the random seeds for the reproducibility and the data set. So how the data set should be stored. So there we used PyTouch. Here it's Keras. So with Keras, we are specifying the MNIST data set. So to load that MNIST data set, and we are splitting into a X train, Y train, X test, Y test, and we are again splitting that training data into training and validation data. So there is three sets of data for the training, validation, and test, and we are returning the data. So this is just load. This is just a load function. So this is a normal function. Also, in our case, in weights and biases, we need to log those data. So there, what will be the changes? The next slide. So this is load and log. So this was just load, and this is load and log. So here, what happens is we need to be telling. So we need to be initializing our weights and biases tool. We can be telling. We can give a project name that we need. So I will give weights and biases, artifacts, and job type is loading the data. The job type is that artifact in which part of the pipeline it appears. Based on that, we can give a job type and which is the project that we are working on. Based on that, we can be giving the project name. So we give the project name, we can give the project run, job type, and make it as a run. And in that, we can be telling load the data sets and have the names as training, validation, and test. Create our artifact. So here, if you see, this is a raw data. Because we haven't done any pre-processing or anything, we are just storing it as a raw data. So we are specifying that to save this as an artifact. So artifacts, like artifacts is a thing in museum, right? Similar to that, we specify these data sets and models as artifacts and stored in a location so that we can, after that, easily retrieve those. So this raw data is being saved as artifact. We give it a name and we give it a type. So this is a data set we specify, and we also give a description about this data set. So we tell that this is essentially the MNIST data set, and that is being split into train, validation, and the test data. And also we give a metadata, so about the table schema probably, and the sources from where we have taken the data, and what is the size of the data. So each of the data set here, be it the training, validation, and test, how much data is there in particular things, so that we specify. So all those details about our data we specify in the VanB artifact. Once we have specified that, we need to be storing this data into our artifact for name and data in our thing. So we specify this as the mode as WB and .npz. So we save those files and we do a run log artifact. So when we do this run log artifact, the artifact will be automatically saved into a weights and biases tool. So this is the whole function. Once we have defined the whole function, we invoke that function.
Got some error in that line callback config, train config.
Which line? Telling about this particular cell?
The last, I think the last cell.
The last code, the last cell.
I think there's a name error. I think.
Maybe the folder name something.
No, the model name. I think it's saved as Keras artifacts.
It's the very last cell, yes.
So I think the built-in model log should be the same as the previous project name, right? To get everything. Like the project names are a bit different, I think, in each cell.
Okay, okay. In the previous code, this code you are telling?
Yeah, this code only. Like first, like in the initial cells, the data and all are stored in the project named artifacts example, right? And in the build model and log part, it is stored in a project called Keras artifacts. I think it should be the same project, right? Because we
Yes,
have
yes, yeah, yeah. So whatever we give here, the project name is and job type is, it should be uniform throughout. Otherwise, it will have a
job
conflict. Yeah.
type.
So here we have they have given the link for that for the artifact that we have saved it. So here there will be no metrics log because there is no model that has been done. We just save our model. So here if we see in the basic information, we will be knowing about this. And lastly, there is this cell called artifact. When you click it, we will be knowing. So the type is dataset. What is the name? What is the version? That's a V0. We click on those. So we'll be knowing about this data set, the API. So they give a API. So we import the weights and biases, we initialize, and we specify the use artifact. With that data set, we can directly be using that artifact, or we can even download it with this. So they give the option of API to use that data. The next thing is the metadata. So as we have mentioned the metadata, so each of this, what is the source? So what is the different sizes for the training, validation, and test? So that is that, the files. So what is the files that we have stored? We have stored the training file, test file, and validation file, and in graph view. So in graph view, we are loading the data, and that is getting saved as this artifact. So all those information will be we'll be able to know with the given link. Once we have that, the next thing is we need to pre-process. So the pre-processing, we do a normalization, we expand the dimensions, and we do a categorical expansion. So all the pre-processing we will be doing. Once we do that, the next thing is the project. So the project, what I have given here. So the project and the job type. So here that was loading the data. Here what we do is we pre-process the data. After the pre-processing, we try to save that as an artifact. So we have done that too. The next thing is we will be doing the steps, everything is true, and we are invoking the function.
So there is a comment from Gopinath. I sometimes get results different even after setting manual seed. So okay.
Sorry, Gautam, sorry. Please disregard that. Yeah. Sorry. That was for Bhavesh. Thank you.
Oh, okay. So here,
yeah, when I fixed that project name error, it is working for me in the last cell now.
Yeah.
At one place, the project name is Keras artifact. In all other places, it's artifacts dash example.
Yeah, the project name should be uniform. We can give whatever name. So whatever name we have given. So if you see here the projects, so what name that we have given, that will get saved inside that. I have named it as VanB artifact. inside that my runs will be saved. So if we specify in the first cell as different name and the subsequent cells as different name, yeah, it will show a error. So here, so the input artifact, now we pre-process that data and store that as an artifact. So again, this is, here if you see the metadata, we have seen that we have expanded the dimensions, normalized to categorical. So these things are done. And again, after the data pre-processing, the data has been saved. Yeah, we have different runs. So there's a data set, the loading the data and pre-processing the data. So this is the graph view. So we have the data set artifact. Now we will be trying to create the model artifact. So we are specifying the model. So this is a Keras structuring model with convolutional linkers. So once we build the model, we can be doing it as with log2. So with log, how it is being done? Again, it's the project we need to be specifying the job and the artifacts and the run. So everything we need to be building the model, create the artifact. So the model that is being created, what is the type of the model, what is the description that we need to be giving, and the config dictionary we can be giving that as a metadata. And this is a before the training the model, this is saving the model. Yes, so we have this link. We'll be going here, checking out a pre-trained model. So we go here, artifacts. We have this model. Here, if we go, we'll be able to know the model API metadata. So in the metadata, we'll be knowing all the hyperparameters, how that is being saved. This initialized pre-trained model and the graph initialization on the model. So we'll be able to know that. Training the model, evaluating the model. Train and log. So everything they have given us both train and log so that we understand what is the difference and the line of code that we need to be adding as the weights and biases code to understand it.
So can you combine artifact logging with sweep?
Yeah.
So you get final models from sweep and not just the hyperparameter combination.
Yeah.
So these two notebooks can be combined, huh?
Yes, yes.
Okay.
Okay. So here I will name again, the project name is, where is it? So the trained model will also be logged. Give some time for the Firefox.
So this weights and biases has these main capabilities, Gautaman, or it is more than this also?
As far as I can see, this is the main capabilities.
Okay. And it is doing better than other tools like MLFlow, TensorBoard, you said, huh?
Yeah.
So if we want to integrate this in CellStrat Hub,
Yeah.
I'm just thinking how that would be done. The dashboard is on WANDB cloud only. So any of our hub developer has to integrate the instrumentation code in our hub projects,
Yes.
and it would be the same process as what you did here, huh?
Yeah.
So there is no sort of systematic integration of this needed in hub. Any hub developer can just automatically start doing it right away.
Yeah.
When I say hub, I mean CellStrat Hub, yeah.
Yeah. So it's similar to this collab only. Like.
Okay,
Just we need
Bhavesh is running in hub directly, he's saying. So Bhavesh, is it running fine in CellStrat Hub? Okay, great. So Bhavesh is saying it's running fine in CellStrat Hub, so that's good.
Okay.
So we can use it right away. We don't have to do any other systematic development of WANDB into CellStrat Hub. Okay. Yeah, I think Bhavesh, that may be a good idea. Pre-install WANDB in all the kernels. And also we can have documentation on our documentation portal, which shows the user how to, instrument their hub code with the WANDB code. Pretty neat stuff here. I had used TensorBoard before long time back, but it was frankly very, very unwieldy. You have to install it, and it wasn't as clean as this one. This looks far more intuitive and clear to use. So Bhavesh, will it need any kind of infrastructure for having this code in CellStrat Hub, or it will work with the? I guess you ran it with the current beta tire or something, so it works fine. Okay, no need for separate infra support. Free tire will also support it, I think, in CellStrat Hub.
Yeah, it has ran the whole thing. So it has given the link. So we train the model. So for that, what is the accuracy, validation accuracy, the epochs, and the validation loss and loss. So how that has been done. So that is told here. And it also gives this hardware utilization. So if we need to be building a huge model and we need to be seeing how the hardware affects it, that too we could be seeing here with this CPU memory utilization and the threads that is being used. It gives the whole network layer, how it is with the type and the parameters. It logs the whole thing in it so that we'll be knowing with each epoch how it is in the artifacts. So the input artifact is the pre-processed data. The train model is saving during this run. The train model we could be seeing here. So there is this pre-processed pre-trained model, which is the Comet, and the train model that is also getting saved. metadata, the trained model, which we could be directly using, and the graph view. The graph view will tell us what are the artifacts. So there are two model artifacts, the pre-trained and the trained model, two data sets, the raw data and the pre-processing data, and what are the different runs. So initializing, loading data, training, reporting, pre-processing. So what are the different runs and how it is. So if we take into account the runs too, we can click this explode thing. So we also be knowing each run, uh, run, what is the naming of that in detailed manner.
Mhm.
So this is about the artifacts.
Excellent. So, any questions, friends? So I'm glad to hear that we can use it off the bat in SelfStat Hub, which is our own MLOps platform, right? So we can already start using it, or our Hub developers can already start using it. And as to creating an account in Wendbee portal, I just did that. I did a single sign-on with my Gmail account, and it worked very fast. And it seems to be free for the free tier, I guess.
Yeah.
So I think this tool looks more extensive, Gautam, and it might be interesting to explore what else weights and biases has to offer, right?
Yeah. The other things, so the main things they promise is, as I told in this slide, these are the 5 things they specify. So if you work as a team, making the reports and experiment tracking and tables is the other tools. These two I found to be very interesting, the artifacts and sweeps.
Mhm.
That's what.
Bhavesh, do you think this deserves to be a pack in SelfStat Hub, or it doesn't seem to make sense as a pack? This is more of a support library
Yeah,
for
it could
introspection.
come in under MLOps.
Mhm.
Like,
Right.
operate.
Now, does it support PyTorch, TensorFlow, of course, Keras?
Yeah,
Does it also
everything.
support classic ML?
Yes.
Okay. So because classic ML also needs hyperparameter tuning, right? So
Yeah.
we can do classic ML. Okay. Any questions, audience? So Gautaman, that's about it then.
Yeah. Stop the share.
Thanks so much. Really interesting presentation.
Yeah.
And audience, I hope you got to try the hands-on part as well in Colab or Hub. Also, it's working, it seems. So any final questions or comments? Right. Okay. So I am sending the SelfStat Hub link to all of you again. So we invite you to use SelfStat Hub for AI learning and development process, and it supports adding of weights and biases code. Okay, so thanks a lot. Thank you, audience, for joining. Thanks, Gautam, and very well done.
Yeah.
Look
Thanks.
forward to your future sessions.
Yeah. Thanks, Kate, for that.